Hello friends, hello students. I'm live again. Last time during the live class, we had a problem in the smart board. Again, we are here with the same problem. Okay, just see we are dealing with some problems on parabola. So this problem you see show that an arbitrary light ray parallel to the axis of a parabolic reflector after being reflected by the parabolic reflector passes through the focus of the parabola. So this is a very practical problem. See, this is a parabolic reflector. Drawing, let me draw it once again. So parabolic reflector is a paraboloid. That means parabola of revolution. If this is the axis of the parabola, if I revolve this parabola around its axis, I get a three-dimensional figure, and that is a paraboloid. So parabolic reflector has a property. If rays of light or electromagnetic energy, if they come parallel to the axis of the parabolic reflector, then after reflection, they all pass through the focus of the parabola. So this is a standard property. Here, actually, this problem show that an arbitrary light ray parallel to the axis of parabolic reflector, after being reflected by the parabolic reflector, passes through the focus of the parabola. So just let us look at this diagram. So this is a parabolic reflector. You see. So here, what happens? You see. This is a parabolic reflector, and this is the axis of the parabola. This is vertex of the parabola. This is focus of the parabola, this point, and this is the axis. This is vertex. This is focus. So if rays are coming parallel to the axis, after reflection, they all meet at focus. Okay, so these parabolic reflectors are very useful device. See, if you look at some microwave towers with telephone exchange buildings. So this is one telephone exchange, this is one telephone exchange, and you will find that there are some parabolic reflectors on the top of the tower. And these parabolic reflectors are used for line of sight communication in telecom networks in a country. So this parabolic reflector at the focus of the parabolic reflector, there is a antenna feed, you can say source or radiator, and there is another parabolic reflector here, and here again at the antenna, at the focus of the parabola, there is a radiator sort of thing. And this antenna system, this parabola acts as a reflector. They are used for line of sight communications. But in this problem, what you have to do, you have to just show that if rays of electromagnetic energy or light, they come like this, parallel to the axis of the parabola, then after reflection, all rays pass through the focus. You can think it is a mirror also, parabolic mirror sort of thing you can imagine. This is a parabolic mirror. So if rays of light come like this, parallel to the axis, then after reflection, they all meet at focus. Reflection means when the ray of light strikes this point, which is on the parabola, then it obeys Snell's law, and after obeying Snell's law, the reflected ray moves like this. And for all such cases, the reflected rays pass through the focus. Okay. Now, when we consider the reflection of a light ray at this point, then what we do? We draw a tangent at this point. So normal to the tangent, which is normal to the parabola, this is the normal at the point of incidence. So when the light ray strikes the point P, the angle it makes with normal at P is the angle of incidence, and angle of reflection will be same because angle R is equal to angle I as per Snell's law. So considering all these things, we will show that the light rays after reflection passes through the focus. Okay, so let us see how mathematically we can show this thing. So let us try to solve this problem like this. So this is the parabola and this is the axis and this is the vertex. Okay, now this is origin, this is x-axis, this is y-axis. An equation of the parabola, let us assume it is y square equal to 4ax. And therefore, the vertex is 0, 0 and focus is lying on the axis and focus coordinate is a0. Now consider a ray of light which is incident on the parabola at the point P, and the incident ray IP is the incident ray which is parallel to the axis of the parabola, that is x-axis. Okay. Now coordinate of P, let us take in parametric form. If y square equal to 4x is the equation of the parabola, then I can write it is a t square 280. Okay. So what is the value of dy dx? Y square equal to 4ax. So 2y dy dx is 2a. So y dy dx is actually a. It is not 2a. It is 4a. Sorry. So it is 2a by y. 2a, 4a by 2y is 2a by y. Therefore, the value of dy dx at t is 2a by 280. That is 1 by t. Therefore, if I draw a tangent at p, then the gradient of the tangent is 1 by t. Now, if I draw a normal through p, then the gradient of normal, if I call it Pn, so gradient of Pn will be minus t. Gradient of p is minus t. Now let this normal line has the inclination theta with positive x-axis. So therefore I can write what we can write? We can write tan theta is equal to t. Tan theta is equal to t. Okay. Now, what is the angle of incidence? So this is the parabolic graph. Okay, and just let me use a different color to indicate the parabola. So parabola is this one. Your curve is parabola, you can say. Okay, so this is the parabola. Now, if this is the parabola, and this line is actually this line, white line is the incident ray, this line. Okay, now since this angle is theta, so this line incident ray is parallel to the axis. This is the axis of the parabola also. X-axis is the axis of the parabola. Therefore, this line makes an angle theta with incident ray. All right. So angle of incidence is nothing. I equal to nothing but pi minus I, which is pi minus theta. Okay. Now angle of reflection will also be I. So this angle is also I, and this is R. So PR is the reflected ray. At P. So this is the incident ray and this is the reflected ray. All right. So this is the reflected ray, you can see. Now this angle is theta. Now this angle is I, because this is angle of incidence. I is nothing but pi minus theta, because normal is theta. So this angle is also theta. So it is I minus theta. I equal to pi minus theta. So this angle is also I, which is pi minus theta. Now let inclination of the reflected ray is alpha. That means inclination means the reflected ray makes an angle alpha with the positive x-axis, this line here. So alpha plus I, you can say theta. So alpha is theta minus I, but I is how much? I is pi minus theta. So theta minus pi minus theta. Okay, so it is 2 theta minus pi. So gradient of the reflected ray MPR is how much? Tan alpha is tan 2 theta minus pi is equal to minus tan pi minus 2 theta. So it becomes minus of minus tan 2 theta. So it is tan 2 theta. Okay, up to this is it is clear. Okay, now tan theta is actually tan theta. Theta is the slope or inclination of this. So tan theta should be equal to minus t, because it is the tan theta is minus t because MPN is minus t. So tan theta is minus t. And tan alpha MPR is actually tan 2 theta. Tan 2 theta is what? 2 tan theta by 1 minus tan square theta. So what we did, from the given equation we calculated dy dx at the point P, which is 1 by t. So MPN, that is the gradient of normal at point P, is minus t. If this angle is theta, then definitely tan theta is minus t. Here it is not plus t, it is minus t. Now this is the reflected ray PR. A reflected ray, if it makes an angle alpha with the positive x-axis, then alpha is actually theta minus I, and theta minus I means pi minus theta. That we have noted somewhere. This theta is actually this theta plus I is pi. So I equal to pi minus theta. So theta minus pi minus theta is 2 theta minus pi. So inclination of the reflected ray is alpha. Therefore, the gradient of the reflected ray, this is the gradient of the reflected ray, which is tan alpha is tan 2 theta minus pi is minus tan pi minus 2 theta. That is minus tan 2 theta, tan 2 theta, 2 tan theta by 1 minus tan square theta. So MPR, the gradient of the reflected ray is tan theta is how much? Tan theta is minus t. So minus 2t divided by tan theta is minus t1 minus t square. Okay. So it is, you can write 2t by t square minus 1. Okay. So MPR is gradient of the reflected ray at the point P is actually how much? 2t by t square minus 1. Okay. Now, what is the equation of PR in this case? Then, what is the equation of PR? So, for that, what we do, these are not required at all at this moment. So, equation of PR is y minus 280. That is a line passing through P and having gradient this much, 2t by t square minus 1. Y minus 280 equal to 2t by t square minus 1 x minus 80 square. So this is the equation of the line here. Okay. Now where this line cuts x-axis, let us find. So put y equal to 0 to find the point where PR cuts x-axis. Put y equal to 0 in this equation. So what is this? So minus 280 y equal to 0 is equal to 2t into t square minus 1 x minus 8t square. So it is t square minus 1, sorry. This is t square minus 1. A t cube plus 2at equal to 2t x minus 2at cube. So minus 2at cube minus plus 2at equal to 2tx minus 2at square. 2at cube. So 2at cube. So these two they cancel. So x becomes 280 by 2t, which is a. So what I get from this interesting result. We get the line PR cuts the x-axis, line PR, that is the reflected ray, cuts x-axis, which is nothing but axis of parabola at point A0. At point A0, because x equal to a and y equal to 0. So A0, which is nothing but focus. So irrespective of the value of p, because for different values of p, I get different points p of the parabola, and if I take parallel rays striking this point, then after reflection at p, the reflected rays pass through the focus. So reflected ray always pass through the focus, which is nothing but area. So it's a very interesting property of parabola. Just we established analytically that when incident rays are parallel to, this is another incident ray, parallel to the axis of the parabola, then after reflection it goes through the focus of the parabola. So this is a very important vital property of parabola. Just we have shown how it can be analytically described. Hope you like this problem. So if you work out this problem, then your understanding on the subject becomes clearer. Okay. So with this I conclude present live session. Thank you very much. See you later. Thank you.